Hey everyone, let's solve the third problem from weekly contest 314, that is using a robot to print the lexicographically smaller string. You are given a string S and a robot that currently holds an empty string T. Apply one of the following operations until S and T are both empty. Remove the first character of S and give it to the robot. The robot will append this character to the string T. Remove the last character of a string T and give it to the robot. The robot will write this character on paper. Return the lexicographically smallest string that can be written on the paper. So let's understand it with an example. Before that, let's understand what lexicographically smaller means, right? So let's say we are given two strings, that is A, B, D, A, and another string A, B, C, A, right? So basically, lexicographically smaller string is that string which will appear in the dictionary. If we arrange these these strings in a dictionary, the string which appears before the other string is lexicographically smaller than it, right? So how do we check dictionary order? So first we compare the first two elements. If they are equal, we move ahead and compare the next two, and then we keep comparing until we get a different elements, and we've got a different element, which is the third one. So we now check which one of them is a small. So it is C, which is a smaller than D. So that means this will appear in the dictionary before this string, right? If we arrange them in a dictionary order. So that means this string is lexicographically smaller than this string, right? So this is what lexicographically smaller means. Now let's come back to the question and understand what the question is saying. Basically, we have a string S and we have another string, an empty string T, right? So now what we are doing is we can perform two operations. We can remove the first character of this string and append it to T, or we can remove the last character of T and write it on the paper. And doing these operations, we want to find the lexicographically smaller string that we can obtain, right? So let's see how this is working. Let's understand a little bit more. So now first of all we will have L here, right? Because we have nothing in the T to remove. Now we have two choices, right? Appending A in here or removing L and writing it on the paper. So definitely A is smaller, so it will not be a good idea to remove L and write it on the paper, because that way we will get this, we will not get a lexicographically smaller string. So to get a lexicographically smaller string, you need to have the most minimum values in the beginning, and we don't care what values are after that. We want the minimum values here, right? Arranged in an order. So basically, it is a good idea to append A in here. Now again we have two choices, right? We have two choices to make, either appending K here or removing A. So obviously A was the minimum out of all of these elements, so it is a better idea to remove A and write it here, right? Now we have removed A from here, alright? Now we have again two choices, appending A or removing this. So again we see that we have another A, right? Another smaller element. So it will be a better idea to have A here rather than A or K. Even though K is smaller than L, it will be better to have AA, because it will give the lexicographically smaller string, right? So we will keep appending, right, until we reach this element, right? We will keep appending until we reach A. Now we will remove this A and write it here, right? Now we will check for C. We will append it here. But now in the next iteration, it will be a better idea to remove C from here than appending D in here, because C is the smallest in all of these elements, right? So we will do we will put C here. Then similarly we will put D here, E here, and then remove the rest of the element, right? So this is the lexicographically smallest string we can obtain in this case, right? So let's see how we will code it, right? Basically, what we need to understand is we are finding the minimum element after we have removed all the elements, right? For K also we checked whether there is a minimum element here. We checked, yes, there was A in here, right? Then again, when we came to, after we had reached here, we again check the same for this part also. Then also this part, then also this part. So basically we're doing it every time. Every time we have to make a choice, we are checking the remaining characters in S. So one way to do it is in O of n square complexity, that is having two loops, one for performing all the operations, and the second for calculating the minimum in the remaining S string, right? So how can we reduce that time complexity? So to reduce the time complexity, we can use something called suffix array, right? We can create a suffix array which will calculate the minimum values, right? For every index, we will calculate the minimum values that will be, there for the remaining array, right? So we'll create a suffix array, right? So let's see how we'll create the suffix array. So we will copy the first element as it is. Then we will check which of these is minimum. So obviously it is D. We will put it D in the suffix array. Then we will check for this part. So it's C. We'll put C in the suffix array. Then we'll check for this part. It's A. We'll put A in here. Then we'll check for this part. We'll put A in here. And we'll keep on doing until the very last element, right? So basically this is the suffix array that we'll get, right? And then we will check, like we can simply take the index, right? Index wherever we are, and using that index we can easily fetch the minimum element for the rest of the array, right? So this will decrease our time complexity, right? It will save us from calculating minimum again and again. Now let's see how we can code it. So basically what we are doing is, so here we have created our suffix array, right? In this part we have created our suffix array. Now we have created a paper string, right? And a stack. Now why we are creating stack is to make the question easier, because every time from the string T we are removing the last character, right? We could have also made string T, but to make things easier we have taken stack, right? Because stack is last in first out. So basically we can easily check s dot top and we will be good to go, right? So then we are iterating inside this. Now what we are doing is we are checking if there is nothing in the stack. We'll simply push ith element, right, of the string into the stack, right, and then continue. Or if there are some elements in the stack, what we will do, we will check if the top element is less than equal to the suffix I, right? If it is minimum, right, if it is minimum, then we will add it to the paper string and remove that element from the string. Or we will keep pushing elements into the stack. And then after we are done with this loop, after we have exhausted our array S and T, we will remove all these elements in descending order, right? And we will put it into the paper string, and then we will return paper string.